Welcome to EEMS 135. This video provides guidance in defining and converting coordinate systems when working with files in EEMS 12, including Grid Plus and EFDC Plus Explorer. Let's get started. Prior to the EEMS 12, EEMS only supported two coordinate systems: the Cartesian coordinate system and the UTM system. The Cartesian coordinate system primarily allows for simulations that require X and Y coordinates of calculation grids with a designated unit in meters, while the UTM system enables processing data overlain on a specified UTM zone. However, both systems exhibit limitations when working with model grids spanning multiple UTM zones. So, EEMS 12 introduces the Geographic Coordinate System, or GCS for short, to handle geographic data more accurately and efficiently. The GCS in EEMS 12 aims to 1. Resolving existing limitations of the currently available reference systems of the Cartesian coordinate system and Universal Transverse Mercator (UTM) system. And 2. Facilitating data processing, where GCS acts as a fundamental projection system. The ability of the geographic coordinate system to define two-dimensional coordinates longitude and latitude based on the Earth's surface not only preserves the accuracy of visualizations of data points under a single projection, but also avoids spatial distortion of the model and data. By default, Grid Plus uses the WGS84 geographic coordinate system. This means that when we create any files from Grid Plus and then export them to external files, their coordinates are in latitude and longitude. We can see the projection settings of Grid Plus in three places in the interface. Firstly, we can access projection settings from the File menu. Secondly, from the Tools menu. And thirdly, from a button in the toolbar. Let's look at an example. Suppose that we have a KML shoreline file of the Caloosahatchee River in Florida, USA. This shoreline was generated in Google Earth. The purpose of using the KML shoreline is to help define where we want to make a grid. After loading the KML shoreline, we can change its properties, such as line thickness and color, to see it better on the map. Now we select the Add New Spline button from the toolbar and start drawing 4 splines. Notice that they need to intersect. Now we generate a grid. For example, we will make a grid of 20 cells by 8 cells from the splines. Next, export the spline and grid layer to external files. When we open them with a text editor, we can see that the files contain projection information, and the coordinates are in latitude and longitude. Grid Plus allows the user to convert from the geographic coordinate system for each file layer, shown in the Layer Control panel, to UTM. The user must define the correct UTM zone number for the latitude and longitude location. We are still using the grid for the Caloosahatchee River. As we have defined it, the river is located in the Northern Hemisphere UTM Zone 17. We can now convert the grid from the geographic coordinate system to the UTM zone. To convert from the geographic coordinate system, select the grid layer from the Layer Control panel, then right mouse click, select Properties option. The grid settings form will be displayed. Select the Coordinate System tab, and then click the Convert button. The form for the coordinate system will pop up. Now, we need to define the correct target coordinate system to which we want to convert. In this case, we select UTM Zone 17 in the Northern Hemisphere. The coordinate system conversion is now complete. We can check the projection information is assigned to the grid layer by exporting the grid to an external grid file. Next, open the grid file with the text editor. We can see that the UTM zone number and coordinates values of grid nodes are updated to easting and northing in units of meters. Note that the UTM zone number will be negative for the Southern Hemisphere. In the case when opening a file generated by a third party, for example, an RGF grid mesh generated from Delft 3D, we will need to define the coordinate system first. In this case, we import the grid by clicking the Import button from the toolbar and then selecting the Import Grid option. The Import Grid form will pop up. Select the proper file extension from the drop-down arrow, then select the RGF grid file and click the Open button. As a result, a horizontal line is displayed in the workspace, and a new grid layer is added to the layer control panel. The file is not displayed correctly as the file doesn't contain the coordinate system information, and Grid Plus doesn't know where it should be located. Next, we need to locate this grid in the right place in the online background map. To correctly configure the grid location, we must define the correct projection for the file. Right-mouse click on that layer, and then select the Properties option. The Grid Settings form will pop up. Select the Coordinate System tab and click the Define button. The Coordinate System form will appear, and we will select the correct projection from this form. The projection should be known by the user. In this case, we select UTM Zone 17, Northern Hemisphere. Once we have finished defining the coordinate system, right-mouse click on the RGF grid layer and select Zoom to Layer. We can see it is now in the correct location. After assigning a coordinate system for the RGF grid file, we export the grid layer as a native Grid Plus file. Put the name for the exported file. When opening the file with a text editor, we can see that the projection and coordinates of grid nodes have been updated. From now on, if we import that grid file in Grid Plus, there is no need to define a coordinate system anymore. EFDC Plus Explorer can work with three kinds of projections: geographic, UTM zone, and Cartesian coordinate systems. Notice that Cartesian is typically used for the experiment model, so it does not have geographic coordinates or a UTM zone. When we create a new model, we can set the projection to the EFDC model. Click the New Model button, and the Cartesian grid generator form will pop up. Next, click the Set button for the model projection, and the coordinate system form will display. We will define the projection for the model on this form by selecting an option from the drop-down arrow. In this case, we select the geographic, longitude and latitude option to create a new model using the grid of the Caloosahatchee River in Florida that Grid Plus previously generated. If we want to create a new model from multiple grids with the same coordinate system, we can check the checkbox Use the same projection for all grids. After selecting Model Projection, we can import a grid from a file by clicking the Import Grids button. The Import Grid form will then pop up. From this form, we select Grid Type and then select the grid file by clicking the Browse button. If we want to import multiple grids at once, we can check the checkbox Multiple Grid Files. Once the import grid closes, the coordinate system form will display again to remind the user. Notice that the projection information shown in this form can be different from the projection in the model projection we set previously, as it is based on projection information from the grid file. For example, to clarify this, we import the UTM grid file of Caloosahatchee River. As a result, the coordinate system form will display with UTM Zone 17, Northern Hemisphere, while the projection in the model projection is geographic. Click the OK button, and the projection in the model projection will be updated as the projection in the grid file. Once a model run is created, EE still allows you to switch between the geographic and UTM zone coordinate systems. To do that, we go to the Model menu and select Project Settings. Or we click the Project Settings button from the toolbar. The Projection Settings form will pop up. Select the Coordinate Projection tab, then click the Change button. The coordinate system form will be displayed. In this case, we select UTM Zone 17, Northern Hemisphere. Notice that from now on, once we change the projection to the model, this change will affect the model output when we run it.